Okay, so welcome to this ACUR at ANU student presentation session. We firstly acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respect to the elders past and present. My name is Max Kirkby and I will be chairing today's session. And our first presenter for this afternoon's session will be Jocelyn Ware. Please start when you're ready.
All right, thanks, Matt. I'll share my screen. Everyone see that, I hope? Yeah, awesome. All right. So good afternoon, everyone. My name's Jocelyn. I'm doing an advanced Masters of Astrophysics at the National University. Today, I'm going to talk to you about obscuration levels in radio and optical data. This study was done as a summer vacation scholarship with the Australian Astronomical Optics. Firstly, let's talk about what radio and optical data is. In astronomy, we can collect data from a whole range of the spectrum of light. These images, so this little graph here shows you 5 different images. These images are all from the same galaxy, just observed in different wavelengths. On the very right here is the X-ray. This is a very teeny tiny little bits of wavelength. And the big one is the radio. So my project focused on radio and visual. Okay, so in this diagram, the optical data is referred to as a visual image. This is because the optical range is what our eyes can see. So it's known as a visual range, but we just call it optical for this project. So data for each of these wavelengths needs to be collected by specialized instruments. The optical data is collected via a mirror-based telescope, similar to the ones you would see at an observatory. The radio data is observed by radio telescopes, which look like big satellite dishes. Optical data is great for studying stars or galaxies that give lots of light. The radio data is used to collect information about darker objects like dark clouds or dim galaxies. So there is overlap between the dim galaxies and bright galaxies seen in visual and radio data. So this project is based on those overlapping galaxies. So but an issue that all wavelengths of light experience is dust. So in astronomy, dust refers to anything that is very, very small. This ranges from tiny bits of rocks, tiny bits of carbon, to tiny bits of ice, just very little small debris around. So dust is really, really important in astronomy though, because it is a building block for everything in space. Without this material, like little bits of material floating around, there'll be nothing to form stars. So for example, on the left-hand side here is the pillars of creation. This is a huge cloud of dust and gas. In the wispy pillars, there are newborn stars and an abundance of gas to potentially make more stars. As you can see, there's kind of very bright areas up here. I hope you can see my mouse. They show new forming stars. So this is known as an active star-forming region. So dust is really, really, really helpful in these big clumps. But unfortunately, dust isn't always in these big clumps, but it is everywhere. And it is really good at getting in the way of things. It's like a big blanket that sort of covers the entire sky. And the effects, so this actually affects all the observations and all our data. It makes galaxies look a lot dimmer than they actually are. This is known as obscuration. So therefore, all data needs to be corrected or adjusted some way to account for all this dust that is obscuring the data. So in my study, I compared radio and optical data to investigate the advantages or disadvantages of choosing radio data over optical data. So these plots were made during the initial investigation into the data. So these graphs look at the data sets in terms of redshift and magnitude. So in astronomy, the term magnitude refers to the brightness of an object. Seems pretty simple, right? Not quite, there's a little catch. So with magnitude, the lower the magnitude, the higher the brightness. So in the graph here, we have a -26 at top and -14 at bottom. -26 is smaller, so all the bright stars at the very top of this graph. There's also the term redshift, may be familiar to you, but redshift is used to tell the distance to an object that is very far away. So these plots show the brightness of the galaxy by how far away the galaxy is. The optical data, as you can see the very top one here, does have a larger amount of data points than the radio data, but that's because there is more information in the optical data set than the radio data set. But the interesting part about this graph is a spread along the x-axis, so all this distance. The data has been cut up into 3 sections, A, B, and C. These are known as volume limited cuts. This ensures that the data that we're comparing has the same average brightness and then take into consideration any particular effects that it may have on observed data that's close and far away from the range. So this discussion around sublimation rates and dust requires understanding of the key concept called Balmer decrements. The Balmer decrements is a ratio of the H-alpha emission line flux to the H-beta emission line flux. The H-alpha emission is the energy that is created when an electron falls from its high energy third shell to its low energy second shell. When the electron falls, it de-excites, which means it loses energy. This lost energy is converted into light. For H-alpha, this emission light is red. So H beta emission is very similar to H alpha, but instead of falling from the third shell, it falls from the fourth shell. So it falls twice as long, and so it actually has a greater amount of energy. So this loss of energy is converted into blue light. So as we know, dust affects blue light more than red light, such that the red beta flux is reduced more than the H alpha flux. This affects the Balmer decrement. So we can say a high Balmer decrement indicates a high level of obscuration, but it's important to note that a high Balmer decrement level doesn't indicate that there is much dust present in the galaxy itself. The Balmer decrement is just showing us how much dust is between us and the galaxy. So these graphs demonstrate the obscuration level for each data set. So these graphs are split into the 3 distinct groups we saw in the previous slide. The red line is labeled radio detected, which is the radio data. The blue line is labeled all, which is the optical data. In the first image, which is plot A, we can see that both data sets have a similar shape and that the radio data has a slightly higher Balmer decrement count, but nothing significant. In the plot B, we have something more interesting happening as the shapes of the data are starting to shift. The red radio data is shifted to the higher Balmer decrement value, so it's now its peak has been moved slightly more to a higher Balmer decrement value, and it continues to have, which is really cool. Then the final plot, plot C, which is the furthest distance away, has the most interesting results. Just going to move that out of the way. The Balmer decrement value has increased again, such that the radio data consistently has higher counts of Balmer decrement compared to the optical data. So on the right-hand side here, we can see that the red line, which is the radio data, is consistently higher than the blue optical data. So this actually shows us that the radio data has a greater obscuration than optical data. This is emphasized at the higher distances. Similar to the last plots, these graphs separate the distances, but these plots look at the brightness of each galaxy. So a quick reminder that the lower the magnitude level, the brighter the galaxy. So low magnitude, bright star, or bright galaxy rather. In the first distance plot, which is graph A, the shapes and values of 2 data sets are very similar. Nothing too interesting green on there, but for plot B, we can see the red line radio data starts to drift as it has higher counts of brighter stars. So it's starting to separate from the blue line here. And the final graph, plot C, which is the furthest distance, shows a dramatic shift in average brightness. So the red radio data has a more prominent peak and has a brighter than optical blue data. So you can see here that the peak of the blue data, if we just draw that line down there, it's going to be like negative 21, negative 21.5. But if you go to the peak of the red radio data, it goes down to about negative 22. So it's a smaller number, the red radio data is more brighter. So these graphs show us that the radio data is more sensitive to brighter galaxies. And similar to the last set of graphs, this result is more prominent in the higher redshifts. And so as dust is inherently linked to star formation, we must also investigate star formation. So these graphs show the result for each data set. So in this graph, optical data is referred to as H alpha, as the star formation rate is calculated by H alpha emission flux. For radio data, the star formation rate is calculated by radioluminosity, hence it's referred to as radio. So the graph on the left shows star formation rate and for radio data and optical data. So you want the data to be as close to that blue line as possible here. Because we want to have sort of an even split ideally, but unfortunately this is an ideal world. So you can see that it's a bit more spread out. There's a bit kind of a clump around here, but it's a lot of range, but that's fine for this kind of data. Is just an initial look. But it sort of does follow what we think should happen, which is really good for us. And the graph on the right shows exactly what the graph on the left has, but actually includes a Balmer decrement value. So the darker the spots, the higher the darker the spots, the higher the Balmer decrement value, which would indicate a higher obscuration value. So all the dark points are at this kind of high area of star formation rate, which is where we want them, which is really good. So the fact that these graphs are very similar to previous published or expected results, it gives us a confidence in what we've calculated correctly. So to summarize, from the Balmer decrement graphs, we know that the radio data has higher levels of obscuration, particularly at high redshifts. The brightness graph shows that radio data tends to detect bright galaxies easily, especially at high redshifts. And star formation rates plots help us gain confidence that we know in our work and that our results are correct. Also, as a fun fact, this particular topic has been turned to a PhD thesis, so choose some exciting insight into this topic in the coming few years. Thank you all for your time today. Are there any questions?
Thanks very much, Jocelyn. There are now 5 minutes for Q&A from everyone, but we'll begin with judges. So judges, do you have any questions for Jocelyn?
Yeah, I do. Thanks very much for your presentation, Jocelyn. I was wondering, so you're talking about 2 different ways of viewing things like stars and galaxies.
Absolutely.
Do you have to choose between them, or is it sort of some ways of detecting them are better than others, or could you just pick both radio and optical and find out different things?
So it all kind of depends on the instrument. So every wavelength, if I just jump back to that original photo that I had. So these are all the same image, but you can see that they have different information in them. So the radio data, so the radio here and the visual, they have very different things you can see. So of course, by having more wavelengths to observe in, you have more data, you get the full story, you can understand its motion and its past and potentially its future. But to actually determine which one you use, it's going to be very up to what's available to you and what you want to find. So again, if it's very far away, you want to use radio data to get those really distant objects. Also, like black holes are typically observed only in radio data. But to know which one to use, each instrument does have each wavelength is a particular instrument, so it can be very restricted to what you can and can't do in these situations.
Yeah, okay. So does that mean that a lot of astrophysics research is sort of limited by the instruments available?
Absolutely, yeah.
Okay, thank you.
Hello?
Oh, hello?
Sorry, I turned my video on. Sorry, I missed the first few minutes of the talk, but I just had a question on the end. You mentioned that this project will be continued as a PhD, right?
Yeah, I don't mind, no. It's done with Macquarie University.
Fantastic. So what do you like to continue doing the PhD? So what are the aims would be, you think?
Oh, for that one, probably further research into just looking what's going on. There is some more data coming out for radio soon, so they should be able to get a larger data set. So the course is always improved, have more data, so better results. I think also looking at potentially, so we use because we're very restricted to what we had available to us, we couldn't actually use magnitude in the R band, only in the I band. So going into the R band, looking at that kind of stuff, is one of the big things we want to get done. So that could be interesting to see those results.
Thank you.
Do the judges have any other questions? Okay, if that's the case, are there any questions from the audience? So either please type your question into the chat or raise your hand so that I can unmute you. So it looks like Jia has a question. Would you like to ask the question?
Yep. Thanks, Jocelyn. That was a really nice presentation. I was just wondering, I mean, I have sort of a naive question to ask, if you don't mind. I was just looking at one of the first plot that you showed, that you have the volumetric volume cut, I think.
The volume.
Yeah, this one.
Yeah.
Yeah. So I wasn't sure if I quite interpret this question correctly, because it seems like on the y-axis that's the brightness, and then would that be the absolute brightness, or is like the apparent?
That is the absolute brightness, I believe.
I see. So it seems like it seems to me that, you know, as we have larger redshift, which means if the stellar object is further away, we have this brighter magnitude. Is that I think it's pretty consistent over here. I can understand what you mean. So at the lower redshifts, we do see more brighter objects. Why that is, I can't quite remember. An educated guess would be it could be it's easy to see brighter objects than they're closer to you. But I don't want to say that's just a guess. So, but I think, I don't know. Sorry. Yeah, so that's what I think would be happening there. Thank you.
Do we have any other questions, either from the audience or other individuals? Okay, it doesn't seem like it. So thank you very much for that fantastic presentation, Jocelyn. And we'll now move on to Sophia Ridolfo. So Sophia, feel free to begin whenever you're ready.
Yeah, can you see my talk?
Yeah, we can see perfectly.
Just the slides, I think. Like not my. Yeah. Okay.
Yeah, we can just see just the slides now. So that's really good.
Excellent. Okay. So hello, everyone. My name is Sophia. I'm a third-year undergraduate studying astrophysics at Australian National University. And today I'll be presenting my research on a study of the star-forming regions in the local spiral galaxy NGC 628 with signals data. So to give you a bit of background, when we study star formation, we typically use observations of star-forming regions called H2 regions. These are essentially the birthplace of stars. They're regions of charged gas, mainly hydrogen, where stars have recently formed. And these young, recently formed stars in these regions emit huge amounts of radiation, which energizes the clouds they're born from, like in this diagram, as you can see. And we observe this radiation as emission lines at optical wavelengths. H2 regions are the primary indicator of star formation in extragalactic studies, and it is for this reason that analysing the properties of ionized gas in these regions can provide a lot of important insights into how stars form and in turn how galaxies evolve. So one particular well-known galaxy that's a well-known target for star formation studies is NGC 628 or N74. And this is a local spiral galaxy, a grand design spiral galaxy, well known for its prominent spiral arms, and is about 9 megaparsecs away. In my project, I use new observations of the star forming regions of this galaxy from the Signals or Star Formation Ionized Gas and Nebula Abundances Legacy Survey. And many previous studies have significantly advanced our understanding of star formation by analysing the properties of the gas in the star forming regions of this galaxy, but we haven't had any studies on a complete catalogue of H2 regions of this galaxy until now. And this is where my data comes in. As I said, the galaxy is very well studied, but the advantage with these new observations from Signals is that these observations are at a high spectral and spatial resolution, meaning we can identify individual H2 regions rather than being lost in the background emission. And the instrument used has a very large field of view, allowing the entire galaxy to be observed. And as a result, we end up with the most complete catalogue of H2 regions for this galaxy ever recorded. For approximately 4,000 H2 regions were identified for further analysis. Having this complete catalogue will be vital in providing a more clear picture of the star formation history of the galaxy and allow us to derive different properties of these star forming regions via emission lines. And in my study, I derived the following properties. Oxygen abundance, ionization parameter, pressure, and electron density. And these properties are all equally important and provide crucial information on the chemical history of the galaxy. However, they're difficult to derive as they can't be directly measured, and so we have to derive them by using combinations of these emission lines. And so the first property I derive is the oxygen abundance in each star-forming region. This is, simply put, the ratio of oxygen relative to hydrogen. And we use oxygen because after hydrogen and helium, it's the most abundant element in the universe, and it provides important clues about the flow of heavier elements throughout galaxies. So there's multiple ways we can calculate the oxygen abundance by combining these emission line ratios, and we use several different diagnostics in this study. So in my study, I use the N2S2, N2H alpha method, an updated version of this method, and the N2O2 ratio. And so I'll present my results for the oxygen abundance in the H2 regions of this galaxy for all three methods. Each data point in these plots here corresponds to an individual H2 region and is color-coded by the oxygen abundance. So lighter data points, for example, in the center of the galaxy, will have a higher oxygen abundance and vice versa. And the plots below show the radial gradient of oxygen abundance, which is essentially the same information as above, but shown in a different way. And the galactocentric radius is the radius from the center of the galaxy. So I'll explain more about the significance of the gradient in a moment, but for now, understand that these different methods of calculating oxygen abundance give us different results, and this is why we need to test these multiple different methods. Now back to the oxygen abundance gradient, the radial gradient. So I've picked one method from the previous slide to explain in a bit more detail here. and overlaid the plot over an image of the galaxy, so you can see how the H2 regions line up with the image of the galaxy. And notice that as you get further and further away from the center of the galaxy, the oxygen abundance actually decreases, or like in the plot before, the data points start out light and they get darker and darker as you go further out from the galaxy. This negative radial gradient is directly representative of the inner region of the galaxy being more enriched with heavier elements, and outer regions, which have a lower oxygen abundance, have less heavier elements in those star-forming regions. So you can see that the radial gradients of oxygen abundance are really important because they directly inform us of the chemical enrichment of the galaxy. And so I also calculate corresponding ionization parameter gradients for each oxygen abundance method, and we found that each gradient was flat. Now these results are interesting, but are typical of an active star-forming spiral galaxy such as this one, and have been calculated for this galaxy before. So my results agree with the previous literature. But two other, so you can see, so you can see as you go out from the center of the galaxy, the oxygen abundance or metallicity decreases. Yeah, so two other properties that we can derive by combining emission line ratios to gain insight into properties of star-forming regions is pressure and the electron density. And this hasn't been calculated throughout H2 regions before, so this is completely new. These two quantities are really important because they directly influence the size and the mass of the largest H2 regions a galaxy can have. And other properties such as oxygen abundance depend critically on the assumptions we make about pressure and density. For example, many models assume a uniform or constant pressure throughout the star-forming regions or throughout a galaxy, but this is shown to actually not be the case. So in my study, I use new theoretical models to derive pressure and density throughout the star-forming regions of this galaxy to provide a more accurate picture of the state of the gas in the galaxy. So in this slide, I show my results for pressure throughout the H2 regions, where each data point corresponds to a H2 region as before, and they are color-coded by pressure. And below is a histogram showing the frequency of H2 regions in particular pressure bins. And what my results show is that firstly, unlike oxygen abundance, there is no clear gradient in pressure throughout the galaxy here. And secondly, in the histogram, we see a very high amount of H2 regions having a very low pressure. These kind of pressures are actually typical of an active star-forming galaxy such as this one. And finally, I obtained very similar results for electron density with no obvious gradient in electron density throughout the galaxy and very low densities for most of the H2 regions in the catalogue. These results for both pressure and density are very interesting as they provide further proof that pressure and density aren't uniform quantities like we previously might have assumed. And in other words, we should kind of expect a result like this because star-forming regions disturb their surrounding gas, and a more active star-forming galaxy such as this one is expected to have an inhomogeneous environment surrounding the stars. Yes, so to conclude, I used emission line data from the largest catalogue of H2 regions for this spiral galaxy, NGC 628, and derived 4 equally important properties. Oxygen abundance, we found that there was a decreasing a negative radial gradient with the oxygen abundance decreasing the further out you go from the galactic center. I calculated ionization parameter and found that there was a flat gradient as typical for star-forming galaxies. I calculated pressure and electron density and found that, interestingly, there was no gradient, which suggests that there's no visible structure to the spatial distribution of pressure and electron density in the galaxy. And so some interesting possible future work that we could do with this is get a bigger sample with more galaxies and apply the same methods I've done here with these theoretical models and the same metallicity diagnostics. I could also study azimuthal variations in metallicity throughout the spiral arms, for example. And I could also derive pressure and density on a sub-H2 region scale, which hasn't been done before. So for example, last year I studied metallicity on a sub-H2 region scale, but pressure and density hasn't been looked at on this scale before. Yes, thank you very much.
Thank you very much, Sophia. Fantastic presentation. There are now 5 minutes for Q&A. Judges, do you have any questions?
Yeah, I'll ask a question. Thanks, Sophia. That was fantastic. You said with your pressure and electron density work, which was new, and you showed that the assumption of a uniform density is not the case, and that it's typical of this kind of galaxy, and that future work could involve a bigger sample. Do you think that could lead to sort of like a generalizable set of assumptions, or do you think it'll be stuff that'll be specific to particular galaxies?
I think it would be particular to particular galaxies. So when I say bigger sample, I probably should have specified, I meant more spiral galaxies. We typically like to study spiral galaxies because in the spiral arms, they're quite, they're known for being very active star-forming galaxies. And so they would be ideal for studying star-forming, they are more ideal for studying star-forming regions. However, you can study other types of galaxies. Like last year, I did look at an irregular galaxy, but you wouldn't be able to make a set of assumptions that applies to both. You probably could look at them separately and then compare them.
So do things become generalizable to specific types of galaxies? Can you sort of, if someone said, well, we're not going to assume it's uniform density anymore, we believe it's now like this, and so does that become a better assumption?
So with the assumption that pressure and density aren't uniform throughout galaxies, that applies to all galaxies, not just star-forming galaxies.
Yeah. So your work should improve all models, but there's still other improvements that can be done.
Yeah, exactly. Yeah.
Okay, great. Thank you. I understand.
Dean, do you have a question?
Yes. Thanks, Sophia. That was great. So excuse my ignorance. So I'm a chemist. So electron density for me is where electrons are localized in a molecule. So can you define that in the context of space? So what does it mean, electron density there?
Yes. Yep. So in this particular context, I look at all of these properties in the context of star-forming regions specifically. So not the entire galaxy, and not just, for example, one particular star. As I mentioned, these regions are like a cloud of this ionized gas, charged gas. And I look at, the oxygen abundance and ionization parameter, and then the pressure and density in the context of these regions specifically. So the ISM pressure, or the H2 region pressure, and then the electron density within these regions.
Sorry, can you remind me what was the number? Like what is the density of? So it's measured in electrons per.
Yes. So
per centimeter squared cubed or something, right? In volume.
Yep. So I've taken out the units here, and pressure here is unitless, logged. But yes, the units that you mentioned, I think that's the correct one.
Fantastic. All right, thanks.
So are there any other questions from the audience? And if so, please type your question into the chat or raise your hand so that I can unmute you. So I think we have a question from, okay. Yep, so the person who has their hand raised, please feel free to ask your question. It seems, sorry, Sophia, we seem to have a question.
Are they able to type it in the chat?
Can you hear me now?
Yes.
Yes.
There we go.
Okay. Sorry. Well done, Sophia. I just have a quick question, and it's about the different techniques that we use to measure metallicity. And you said they give different results. Maybe you mentioned this, but why is that?
Yes, so the methods, so I didn't go into a whole lot of detail because that's probably another presentation in itself, but I used different diagnostics, and these diagnostics are different combinations of emission lines. And these actually require, so these diagnostics, another word for them is calibrations, and they're calibrated based on data that we already have to help us inform our models that we already have, and then in turn we can use those models to fit that to observed data. So we're constantly improving them, and that's why I mentioned I had in one of the methods I used to calculate metallicity, I used an N2, S2, N2 H alpha, and then I used an updated version of that my supervisor just sort of came up with this year. And so that's why I included it as well. I included both for comparison. And you could tell that the more updated one it was updated because they used updated S2 emission line data to help inform that calibration. And you can tell that if you remember, the two different gradients did look slightly different, and it was definitely smoother with the updated one. Yeah.
Okay, that's all the time we have for our Q&A. Thank you very much, Sophia. We'll now move on to our next presenter, Jocelyn Ware. So please feel free to begin whenever you're ready.
Yep, thank you. Can everyone look at my see my screen? Yep, cool. Okay, so hello everyone. Welcome to the talk. Today I'm going to talk about the mystery of orphan H2 regions. Where are the ionizing star clusters? So this is done part of my my undergrad honors thesis in the Australian National University. And so without further ado, I'll just start off by talking a little bit about what I'm going to talk about today. So in the next few slides, we'll be going through some introductions and backgrounds, some motivations, and then I'm going to talk about the data, and then the method on how we're going to do our science, and then also the result. And so to start off with a background, just a general description of star clusters without going into too much detail. A star cluster is basically, well, a collection of stars. It provides information on the history and the evolution of the galaxy. And star clusters plays an important role in our thesis because we are interested in the young and the massive stars in these clusters, which are responsible for the creation of H2 regions. Now, what is an H2 region? An H2 region is a region of ionized hydrogen. It is usually a site where stars are recently formed, and that is because, also mentioned by Sophia earlier, that star formation usually takes place in the cloud of neutral hydrogen. And so when a star is formed, it creates a really powerful radiation to the nearby surrounding, and so it ionizes the hydrogen around. And so in astronomy, we call ionized hydrogen as H2, and that's why it's called an H2 region. And so it has a characteristic pinkish red color, which is best illustrated in this diagram. So the Orion Nebula is one of the best example of an H2 region. What we see here is these blue dots that are the trapezium clusters, which are responsible for these ionizing this really, really beautiful region that we are looking at right now. So yeah, we've talked a little bit about H2 regions. We now know that H2 regions are regions of ionized hydrogen. We also know that star clusters are basically the ionizing source of these regions. And so we're going to talk about what's the motivation of our thesis. So what we hope to understand through this thesis, or what we hope to contribute to the understanding of the cluster and H2 relation, is that we could start off by saying, what is it important? So it's important. I'm going to give two examples. So the first example would be in cases where clusters cannot be detected, which is when galaxies are really far away. We were able to actually study the spectrum of H2 regions because it is just many times bigger than these clusters. And also it allows understanding of how clusters interact with their environment, which is in itself a very important field in astrophysics. It helps a lot in understanding theories and simulations. And so now we talk a little bit about our project. We'll be looking as well as NGC 628. It has a large apparent radius. It is face-on. It has a really well-defined spiral arms. And more importantly, it is a target of two important surveys. So the signal surveys, which was also mentioned by Sophia earlier, it observed 4,000 over H2 regions in this green field of view, but it also appears in the LIGUS survey, which has observed 1,000 over star clusters in the LIGUS field of view. And so you can sort of see where this is going right now. So what we do is we combine the young star clusters in the observations of LIGUS, and also the H2 regions in the observations of signals. We put them together and we ask ourselves what connections can we draw out of them. But before doing that, what we find out is that the combined catalog doesn't really make sense. So what I want to draw your attention to is by looking at this legend. What I have here is these gray circles are the H2 regions, and also we would have these blue dots as young star clusters. And so what we expect is sort of what's happening here. So if I have my laser pointed up, what happening here makes sense, because if there's an H2 region, we see a star cluster that is in the region, so it's responsible for the ionization of that region. But also what we find is the majority of these regions here that are empty, that are simply empty. And so that sort of origin, that's the origin of our thesis title, the orphan H2 region. That's just a name we give these H2 regions that do not have their parent star clusters. And it is really bizarre if you think about it, because so like a really nice analogy that is really similar to what we're observing now is that a region that do not have star cluster is sort of similar to when you see a room that is well lit and well illuminated, but you do not see the light source in it. So it really doesn't make sense, right? Like if a room is really bright, it should have something that's illuminating the room. And so that's sort of what's happening now in our combined catalog. And we find that up to 60% of these H2 regions do not have any associated star cluster. And so that is a really big concern, because, is this telling us that, there's a flaw in our star formation theory? Is there a flaw in how we understand how star clusters in H2 region work? Or is this simply just an indication that, studying cluster H2 region relation at high resolution is not a reliable way? And so that begins our analysis. And I'm just going to include one of the major part of the analysis because of time limitations. And so that is because we are saying that these star clusters that are responsible for the H2 regions are too faint to be picked up. So it produces an H2 region, but the cluster itself is too faint to be picked up by the Ligerson survey. And so the other way of asking is, how complete is actually our star cluster catalog? And we say, how many of these young star clusters that are undetected by Ligers can actually create a detectable H2 regions by signals? And the way we do that is by, the way we do our completeness analysis is by using the SLUG code. So SLUG is the stellar population synthesis code. It's amazing. It allows us to create star clusters in our computer, and then we can actually analyze the properties of these star clusters, such as their age, mass, the ionizing flux. And what we do is we synthesize a library of 100,000 young star clusters. We put them into an algorithm that checks if this cluster itself will create a detectable region or not. And then we check again if this cluster will itself be detected or not. And so we plot our result on this plot. I'm going to sort of talk you through. And so what we have on the x-axis is the age of the star clusters, and on the y-axis would be sort of the luminosity of the H2 region. And this limit is how well the signals H2 region survey can detect. And so naturally, clusters with a detectable region will fall in this section, and the ones which are not will fall in this section. And it is really amazing because we find that there's so many gray dots above this point. Now remember, so a gray dot, which means that the cluster itself is undetected. And this means that these gray points are clusters that itself undetected, but can create a detectable H2 region. Now it sounds really, really surprising and interesting at first, but ultimately we realized that that is actually just because a difference in the sensitivity of our instrument. So the cluster instrument couldn't pick up most of them, but then the H2 regions instrument can detect these regions. And so with our simulation of a 100,000 star cluster, we find that 52% of these clusters will not be detected, but it can produce a detectable H2 region. And so this is sort of, we sort of explain why and what's happening before combined catalog. And it's awesome because the physics is not broken. Everything we know is still fine. It's just because the instrument, there's a gap in the sensitivity. And so to make a conclusion, to summarize of what we just talked about earlier, we first combine the catalog of H2 regions and star clusters in an attempt to understand the cluster H2 region relationship. And then what we find is that most H2 regions lack ionizing star clusters, which was very worrying. And then we find out, we use SLUG to understand that it is actually the completeness of the star cluster catalog that is causing these H2 regions that have no star clusters in them. And the mystery is solved. And that's really awesome. And so what can we do in the future? It'll be, first of all, we want to understand the field star cluster, because as you can realize, as you can see, there is actually not only do we have empty H2 regions, we also have star clusters that do not have H2 regions around them. And that's a completely different phenomena that's actually easier to understand, because that can happen if, for example, a star cluster is in a region that is so dense, that is so less dense, that the region has very low surface brightness that is not picked up. And then what we can do next is actually understand how does this property correlate with the H2 regions. For example, if we actually see younger star cluster would have brighter H2 regions, and how we can actually correlate them. And then finally, we hope to help the future surveys that intend to study this relation. We see what we can do to understand, to reduce the number of orphan regions, because if we're seeing 60% of H2 regions not having any star cluster, then, you know, if surveys in the future would want to do something like this, then it's not quite reliable, so to say. So that's it. That's my presentation for today. Thank you, and I welcome any questions and suggestions.
So thanks for that great presentation, Joey. We'll now open up for 5 minutes of Q&A. Judges, do you have any questions?
Did you want to go first, Nadine?
Yes, thanks. Joey, thanks. I just want to ask you, so you mentioned the H2, so what is the, so this is an ionized hydrogen. What is the charge on the hydrogen?
Yep, so it's basically just, you can sort of say it's just a proton, because the electron gets stripped off. So it's just an ionized hydrogen. Yep, H+. So H+ in chemistry is H2 in astronomy. That's just, that's just how it is. And we sort of have to cope with that.
Great. So the orphan regions that you refer to, so these results are from simulation, right? So I'm just wondering, I mean, I don't know, it's just completely, maybe it's only me, but so the graph that you showed before, the one that you, yes, this one. So this one is a simulation, is not a real data experimental, right?
Yep.
Can you explain in a simple terms, like how does the simulation, what do you use to do the simulation?
Yep. So what happens in the simulation? That's a great question, actually, because I was contemplating if I should put that in, because that sounds really technical sometimes. But what happens is that this simulation basically creates a library of star clusters. And then I would have the H, the mass, and also the ionizing flux of these star clusters. And so what I do is I take these ionizing flux. So the difficult part is actually this part, where I convert the ionizing flux into the luminosity of the H2 region. And that actually involves a lot of equations. But yeah, that's how it works. Yeah.
Yes. No, thanks.
No.
Thanks, Joey. That was a really great presentation. As I understand it, you kind of figured out that the catalogue of those is incomplete, and so you've kind of gone from some unknown unknowns to some known unknowns, if that makes sense.
Yep.
And I hope I got that right. And you did sort of mention this in your future work. I was wondering if you tell me more about, does this mean that maybe a new survey that overcomes some of the limitations of the existing surveys is justified? So what might it mean for future surveys?
Right, so that's a great question, actually. So that is sort of the thing we also we hope to understand, because definitely if we want to build something that is really sensitive that can cover 100% of star cluster, it is not possible, because first of all, there's financial issues. Like you have to build a really good telescope, you have to get telescope time, and people would actually want to. It's more like if I observe 3 more days, I can get 5% more data. Is it worth to give that 3 days to you? And also another question would be, identifying star clusters in these surveys are done by a combination of machine learning and also human work. So you need someone to identify these star clusters. So the reason why there's so much sort of incompleteness is because they did a magnitude cut. So they only sort of make visual inspection on clusters that are brighter than a certain magnitude. And if what I've done is if I were to decrease the magnitude to include even more star cluster, theoretically we can decrease the orphan regions from 60% to 30%. That's awesome. But then who will spend like 5 or 6 years just to identify these star clusters? So yeah, I mean, it is sort of a balance of how well we want to do and then how much human power or money power we actually have, if that answers your question.
Hopefully there's some good job creation schemes for astrophysicists then.
Yeah.
Thank you very much.
No problem.
So are there any questions from the audience? And if so, please type your question into the chat or raise your hand so that I can unmute you. No, so it seems like everyone's pretty happy, which is great. And so that brings us to the end of today's session. Thank you to our judges, Catherine and Nadine, and congratulations to our student presenters. You all did a fantastic job. So this recording will be made available online following the completion of the conference. And we also hope to see you in the other sessions throughout the remainder of this week. So thank you, everyone, and have a great day.
Thanks for organizing.
Thank you.
Thank you.
Thanks, Max. Well done, everyone.
Thank you.
Thank you.
Thank you.